Hi everyone, I'm Brian Swingle, and this is a video abstract for our paper titled Building Holographic Entanglement by Measurement. I want to thank my awesome collaborators without whom this would not have been possible. That's Jonathan Jeffrey, Lucian Gandarias, and Monica Schleier-Smith. In the paper, we show how states with holographic patterns of entanglement can be prepared in constant time using programmable interactions and measurements. But what is a holographic pattern of entanglement? To explain, let's take a little detour to thermodynamics. Ordinary matter, when you heat it up, acquires a thermal entropy proportional to the volume of space occupied by the matter. This is a rather generic phenomenon, but there is one interesting exception. If you pile up too much matter in one place, it inevitably collapses to form a black hole. Now we have good reason to think that such a black hole would still have a thermal entropy, but weirdly, that entropy is now proportional to the surface area of the black hole rather than to the volume occupied by the black hole. By invoking the connection between entropy and information, the weird entropy of black holes led to the idea that gravity is fundamentally holographic, somehow encoding a volume's worth of stuff with an area's worth of information. This holographic principle is best understood in the context of what is called holographic duality, or the anti de Sitter space conformal field theory duality, ADS-CFT for short. According to holographic duality, a bulk gravity system is secretly encoded in a lower dimensional boundary quantum system, and the formula for black hole entropy gets vastly generalized. Rather than thermal entropy, we now talk about quantum entanglement, and according to the Ryu-Takanagi or RT formula, the entanglement entropy of different parts of the boundary quantum system are precisely related to the area of minimal surfaces in the bulk. We can get a simple picture by thinking about a disk. If we think of this disk as space, then it has a boundary and a bulk. The boundary is where the quantum system lives, and the bulk is the gravity. Moreover, in ADS-CFT, this disk is warped in that it looks like one of Escher's famous prints, where each angel and demon is the same size. This geometry is called the hyperbolic disk, and it's important because this disk is dual to the ground state, or lowest energy state, of the boundary quantum system. And then from that it follows, via the RT formula, that entanglement entropies in the boundary ground state are computed by minimal curves or minimal surfaces in the disk geometry. This disk geometry therefore exemplifies one particular pattern of holographic entanglement. Our goal in this paper is to provide a procedure to take any geometry and convert it into a quantum state whose entanglement properties obey the RT formula in the chosen geometry. We want to do this for any number of reasons, but one very important one is a desire to realize holographic patterns of entanglement in the lab. If we can do so, then we can study them in experiment and learn new features of holography, black holes, and quantum gravity. Our procedure is particularly simple, requiring only programmable interactions and measurements, and it is able to prepare the desired state in a constant amount of time. That is, a time that does not scale with the size of the system. The paper focuses on a Gaussian setting for its theoretical and experimental tractability, but we also discuss potential generalizations. The main idea is shown in Figure 1 of the paper, which I reproduce here, for which the chosen geometry is the hyperbolic disk we discussed earlier. On the left, we have a graph discretization of that geometry. Our protocol calls for a quench experiment in which the nodes of the graph are coupled together according to the edges. Following this quench, we measure all the bulk nodes, that's the stuff in blue, to produce a pure quantum state on the remaining boundary nodes, the nodes in green. On the right, we show some diagnostics, in this case the entanglement entropy we talked about earlier, and a generalization called Renyi entropy, and establish that they can both be fit with the behavior predicted by the RT formula. In Figure 2 of the text, again shown here, we have another graph that we've obtained now from a different geometry, a wormhole geometry. This geometry now has two boundaries, and these two boundaries are connected by what is in essence a tube. We can again compute the entropies, and we again find that they compare favorably with the predictions of the RT formula, now in this wormhole geometry. In Figure 3, we show another generalization of the basic quench and measure protocol involving what we call decoration. We recover the agreement with the RT prediction and are able to realize a new feature in which some observables have correlations that depend on a power law of the distance between them. This property is also shared with holographic systems. Finally, in Figure 4, we show how, by considering a problem of bulk reconstruction, one can detect a smeared or fluctuating version of the RT surface itself. This is done by attaching probe sites in the bulk and measuring their mutual information with different parts of the boundary. In summary, we have devised a new, simple protocol for repairing states with holographic entanglement. In its present form, this protocol should be experimentally feasible in a variety of systems, including ensembles of atoms in an optical cavity and systems of photons. There are also many exciting theory questions to explore in the future. So, thanks for listening, and please enjoy the paper.